Good morning, everyone. At the beginning, I was talking a little bit about what's going to happen, what's going to happen today, and then what's going to happen on Monday. Today, we're just going to finish 16.3. I've decided that that's the best way to do it. So we'll get a lot more practice at questions from 16.3 than perhaps we might have expected. This is just basically the summary from last time. And the last, 5-10 minutes, we'll talk about the test. So the test is only going to be in 3 sections, essentially. So let's just do a quick run through. If you have a conservative vector function or a vector field f, then this property has to be true, that the partial derivative of this function with respect to y has to be equal to the partial derivative of this function with respect to x. If it is a conservative field, then we can get the line integral by essentially finding the potential function at the end coordinate, take away the potential function at the start coordinate. And this here shows us how we calculate the potential function. We basically use the fact that the gradient of f, delta f, is equal to f. And I just realized that these are vectors, aren't they? On the other hand, little f is just a normal function. And we also mentioned that this happens. And I got a little pretty picture with the same basic idea. So what we're going to do is just practice examples of that happening. So this is my first one. Imagine we have a vector function, this guy here. It's going to be x cubed, comma, y cubed. And the curve C is going to be y equals 2x squared. And it's going to go from the point 1, 2, and it's going to finish at the point 3, 18. Okay, so that's pretty much all that you need. So we are going to find, well, the first thing we're going to find is that guy, and we're going to do it by using this property. So we're going to find the potential function. Oh, I don't. I'll do this version today, I think, at least for this question, this notation. Okay, so not the worst looking function in the world. Would you agree it would be just a simple power rule plus some arbitrary constant that contains a y? By symmetry, plus an arbitrary function, constant function that contains an x. And when you put these together, you have your potential function. That look good? So what's going to happen next then, because that's basically question A, find f of x, y. They have, sometimes they split it in two like this. And then they ask you to find that fella, or they'll ask you to find that fella along some curve C. Is there any difference between those two questions? No, it's the same question, they're just phrasing it this way or that way. So what have we got here? Well, it's the potential function, I'll just call it at the end, take away the potential function at the start. In this question, the start and end are here. So we're going to find the value of the potential function at the point 318 and subtract the value of the potential function at 1, 2. And this is the guy that we've got. So it's going to be 1/4 3 to the 4 plus 1/4 18 to the 4. Take away 1/4 1 to the 4 plus 1/4 2 to the 4. And at this point, I'm not risking my mental arithmetic. Can we just say it's a number? Is it okay to get 0? 42, 170, yes. Negative 42, 170 is yes. So do not be surprised if some of the questions are ugly. Are we comfortable with this process? Vector function, curve. Find the potential function, which is the name we give to this guy. Okay, let me do a variation of this question, just a tiny variation, because I'm not going to do much. Imagine they didn't tell you that. They told you that instead. Right. When you plug 1 in, oops. Right, you plug 1 in for x, and then you would get the y value, 2. And then you plug 3 in for x, and then you'd get that guy. So can you see how this information can be translated into the coordinates of the start and the coordinates of the finish? Now, suppose same story, but the curve C is now given as t squared plus 1, t cubed minus t, and t now goes from 1 to 2. In that situation, don't you plug t equals 1 and that gets you the coordinates of the start, and t equals 2 and doesn't that get you the coordinates of the finish? So you could be given the start and finish by just being told the coordinates. You could be given the start and finish by being told the equation and the x's to use. You could get the start and finish by being given a parametric equation of the curve and the start and finish t values. All of them end up telling you the start and finish point. So just to be aware of the different ways in which they can make your life a little bit more awkward. I think I did that one. I believe I did this one. You can tell me if we've done this one. Yeah, I did that one. It came to my mind. I don't need to ask you. I remember. Don't know if I've done this one. Does that look new to you? Right. So this one is essentially a kind of bigger version of the typical two-dimensional. You agree that's a three-dimensional vector field. So everything's going to be like one more dimension. What are we given? In this case, we're given a space curve, and it's a t squared, a sine t, and a t. Okay, and we're given that. So that's pretty much everything we need to know, right? And you're going to find the potential function, little f, and then we're going to do the line integral from there. So delta f will equal f. In this case, we have 3 of them to deal with. And I'm just going to dot, dot, dot it because it's these guys, right? So the first matchup is that. Okay, what would you get if you integrate this expression, but with in terms of x?
xy squared sin z.
Yeah. And as a placeholder, some function that doesn't have an x in it, right? Then we try the second one, which is this fella, and we get 2xy sin z. And if we integrate this fella, don't you get add 1 to the power, reduce the power by 1, and we get this guy plus some function that doesn't have any y's in it. And then the last one of the set well, if you integrate this one, don't you just get positive xy squared sin z plus a function that doesn't have any z's in it? And we got really lucky here. Would you agree that the overlap is just one expression? You agree it's the same thing? What would I have done if this had plus an x? Suppose this one had all of that plus an x. What would be this fella then?
It would be the same thing plus an x.
Right. And if this had a y cubed in it and this had a yz in it, wouldn't you just add, you know, you just look at it and you basically say, if I put them all together, what would I have? But you don't put them together and say you've got 3, right? You've got them, it counts as 1, right? Everything counts as 1 of the thing. Now, in this case then, I think they're calling it that version, but it doesn't really matter, right? We're going to be evaluating this function at a start and a finish, right? So there's the end, and there's the start. And isn't that where this comes in? So we plug in 0, and we get nothing squared sine of nothing, nothing, which is basically 0, 0, and 0. And then we plug in pi, and we get pi squared sine of pi, and pi. Are we good with that? Right, so we are going to find the value of the potential function at that point and take away the value of the potential function at that point. And this is the potential function. So what have we got? Pi squared? No. Oh, cool. What's the answer?
0?
Yes. I thought I was going to have to do some messy calculations, but that guy there, doesn't he kill off that expression? It's 0. And this one is definitely 0. So 0 take away 0, the answer is 0. So if this particular vector field had this curve passing through it from t equals 0 to pi, the line integral, which is this, which is also the work done in going from here to here, would be 0. So you'd be basically on a net 0 situation. Like you go up a hill and then you come downhill. That's kind of cool. What happens if I had a space curve, whatever it is, and it was 1, 2, 3, and the other one was 1, 2, 3? So you started at the point 1, 2, 3, and you finished at the point 1, 2, 3. I know what the answer is, and I didn't even need to do any of this.
Wouldn't it also be 0?
Yes, because if it's a conservative field and you start and finish at the same point, isn't the answer always going to be 0 when it's a conservative field, right? You put that caveat in, right? Because if it's not a conservative field, who knows where it could equal, right? Well, I guess in this case, you wouldn't be able to do a potential function, right? You'd have to do it parametrically, right? You wouldn't be able to do it using this technique, because this technique assumes that it is a conservative field, right? You can't, you might mathematically be able to figure out an f, but that f would not be usable, right, in the context of the story. Yes, Ben?
Will we eventually be able to solve non-conservative fields?
Yes. And without kind of spoiling the end of the movie, Green's theorem will allow us to do that. Right. You can imagine you'd need something, right? How do you do it if it ain't conservative, right? You still want to know, right? So there must be a way. Well, there is a way. You can do it parametrically, right? But we're already saying, isn't that kind of cumbersome? It's got a lot of work in it. And sometimes the math is so ugly, you're not even sure you can get the answer. This is kind of clean, isn't it? If it's a conservative field. Green's theorem also allows you to get the answer, but in a way that I don't think anybody would predict. So when we show you Green's theorem on Tuesday, you should be looking at it and thinking, what? How did that happen? So let's see. Well, we got. Is there any homework question in? Try to get the number here. In 16.3 that you were doing and it wasn't working out, because that might be a good one for me to do next. Now that could mean you haven't had any problems, or it could just mean you haven't done the question yet. Okay. Just try to find, is it a conservative field, if I can. Let's pick one. Is that a conservative field? That's all the question's going to be. So your answer is yes or no, right? What's your gut feeling? We're going to do the math, but what's your gut feeling? Do you think that's going to be a conservative field or not?
It will be.
I agree. What about it that led you to that correct conclusion?
Math in my head.
Oh, you did it in your head. That's a good skill set. Do you notice anything about the shape of this?
You have an X and a Y on both sides that are separate from the group, and then the group that is combined has equal amounts of both X and Y. So if you took the
What do you differentiate this fella with to check that it is a conservative field?
Respect to Y and then respect to X.
So when you look at a thing and you want to check is it a conservative field, see the first thing, any X's that are on their own you can totally ignore. And in the second one, because it's differentiated with X, any Y's that are on their own. Now, if they're attached to an X, you can't ignore them. That means to me that would be a conservative field. because all you focus on are the guys that have a y and the guys that have an x. Does that make sense? Because if you are doing a partial derivative and it's with respect to y, won't all the x cubed sine x e to the 10x's, won't all of them basically disappear as 0 and have no effect? And the ones in the second group, well, won't all the 10y's and the e to the y's and sine y cubes and all that kind of stuff, won't they have no effect either? So you can actually look at your original vector field and do a kind of surgery on it. So as an example of how I might do that, suppose I was doing that or something even uglier. I would say, don't care, you've got an X. Don't care, you've got a Y. Isn't that the only guys I need to check against? And if I differentiate this with Y and I differentiate this with X, do you see it matches? So just a little trick of the trade that you can actually tell, right? Whether something is going to be a conservative field by only focusing on the things that don't have X's and the things that don't have Y's. Which means I don't need to do, can you imagine if you didn't, wouldn't you do that? Well, I'm not sure you would do that, but you know, you could get a whole load of work that's not necessary. Anything else we can try here? Okay, got this guy, got this guy. Let's find a conservative field for it. Well, let's find it, not the conservative field, let's find potential function. Thinking too quick for my own good. You do the first one, you do the second one, and you do the last one. This fellow becomes 1/2 x squared y. This fellow becomes 1/2 y squared z. And this fellow becomes 1/2 squared x squared z. This one has a function that doesn't have x's in it. This is a function that doesn't have y's in it. And this is a function that doesn't have z's in it. And although they, question?
On the last one, it should be z squared, not x squared.
Thank you. You're right. Although these guys here don't really do anything, right? We never really use them, they're placeholders. They're kind of like, you know, in Calc 2, when you forgot your plus C, you lost a point. If I don't see it in working, I'm going to take a point off you, right? So we want to keep you rigorous in math, right? Now, in this particular one, would you agree that the potential function is actually made up of 3 separate things? So in a lot of potential functions, don't you get a lot of overlap? But not in this one. I don't think this helps much. I guess it might help a little. But you agree that function, you're pulling out a half might save you 10 seconds, right? It's not going to make a big difference. In this particular question, isn't that the start and that's the finish? So don't I just plug in 1, 2, 3, take away 3, 0, 1. And it's finished. I know we don't know how to prove that a function is a conservative field if there are 3. I mean, you can go online and find out how you can do that. Why do you think I could look at that and know that it's going to be a conservative field? There's something about the shape that is here that kind of lends itself to being a conservative field. Anything that comes to mind?
You can almost see a looping pattern. You have with the X, you have an X and a Y. With the Y, you have the Y and the Z, and with the Z, you have the X and the Z. So it kind of like makes a loop.
It's got a kind of circular logic. I don't know if symmetry is the right word, but I can't think of a better word. It has a kind of symmetry to it. Conservative fields don't always have symmetry, but if you do have symmetry, there's a very good chance that you'll be a conservative field, right? So it's that kind of logic. So if I had an X squared comma Y squared comma Z squared, you know, for example, I'd be pretty sure that would be a conservative field. If I had a whole jumbled up mess in each of the 3 pieces, it might be a conservative field, but my gut feeling is that more often than not, it wouldn't be.
Mr. Robertson,
Yes.
I think your answer for the gradient of f is incorrect because, like, when you again, so do you see that f equals part? So when you differentiate with respect to x, you get x, y. Wait, can you move your hand? You get x. You get xy plus 1/2 z squared. That's not x. That's not xy though. Again, partial differentiate.
Oh, if you differentiate this fella,
Yes.
don't you get 2 times a half and you're left with xy?
Yes.
So I'm not sure what you think I'm not doing right now.
Again, if you look at your function, there's a part that says 1/2 xz squared. If you partially differentiate it with respect to x, you get 1/2 z squared.
Oh, this one here?
No. Scroll your finger down a bit. No. Down. Down. Yeah, that's where it is. No. A bit up. A bit up. One. Do you see that? Yes, that's it.
Right. So you think what's wrong with this?
Because if you partially differentiate with respect to x, you get.
Ah, but you
1/2
don't.
z.
This one you do with z. So this one works. You're pausing. I don't see a mistake here. I think I've done this correctly. Does anyone else see the mistake that Reese is trying to point out to me?
There's no mistake.
Okay, it's probably the fact I've got a squiggle here and it looks like there's a number and it's just distracted the heck out of you. If I do it on its own, that piece there came from, no, darn it, I did it again. That piece there came from here. So if you integrate it, you add 1 to the power and divide by the new power and you get that. And I'm pretty comfortable that that's correct. Also, when you look at this answer, would you agree it's got that kind of symmetry, cyclic symmetry thing where the X's and Y's, each one is missing one of the 3 letters. it has that kind of symmetry to it, which makes me feel that it's correct. But I have been known to make mistakes, so it is worthwhile to mention it in case sometime in the next 10 minutes I'll probably do it again. Okay, I got pretty much that guy is finished. I'm not wanting to do any more because I don't think it's helpful, right? So what we're going to do is just start talking about a little bit about your test.
Shall we take roll?
Good idea. Why don't you take the roll? Say hi, everybody, while I'm getting myself organized. Stop sharing for a second. Uh-oh. Do you know that Zoom 5.0 is here? I am not updating until today is over. I am not risking something bad happening. But evidently Zoom 5.0 is here. Can I suggest that you play safe like me and don't upload your Zoom until after the test, just in case, you know. I just
upload
get
our work
worried.
after the test.
Hmm?
Do you mean upload our work after the test later?
No, I
Or-
just mean there's a new version of Zoom out. When I was going out to, get myself ready, and this thing said Zoom 5.0 is here, update now. And I'm just saying, don't update now. When you update Windows 9 times out of 10, it's totally okay. And then 1 time out of 10, your printer stops working and your graphics card goes wonky on you and you spend 2 days fixing it.
I remember when that happened to you.
Okay.
Very
then,
recently.
Right. Well, can you understand my worry about updating Zoom 5 till after we definitely need it on Monday, right? I got to see you in the test and I got you upload and all that good stuff. So I'm not, I suggest that you don't update your Zoom as well, right, to see me until Tuesday. And then whatever can happen then. Okay, so let's talk a little bit about your test. It takes 1 hour, as you know. It's going to have 3 sections, 16.1 vector fields, which I remember wasn't really a lot in 16.1, was it? Wasn't a lot. There was some pick pictures, but don't you just go on and you use the software that you plug the function in? So you can imagine any questions you get from there will be quite superficial. Although line integrals 16.2 and fundamental theorem, what we've essentially finished now, 16.3, they are going to have some heavy duty questions in them. So when you're doing 16.2, you have to do it the parametric way. Even although you could do it the quicker fundamental theorem using potential function f, we're testing, do you know how to do the parametric versions? And some of the questions in 16.2 could be very, very easily done knowing the fundamental theorem, but aren't so easy to do, right? So give you an example. Imagine I gave you a vector field and you did an entire circle, right? An entire orbit of a circle was your C. Wouldn't the answer be 0? But you got to prove it to is the old-fashioned way, right? So bear in mind that when a question is 16.2 and it's a line integral 16.2, which will essentially be the middle questions, then that you must do them that way. Now, do you want to use the fundamental theorem as a check that the answer is 42? For sure. I don't mind you using another technique just to check that the first one works, and that's okay. And then when you're doing the fundamental theorem, I don't think anybody's going to do it the parametric way, right? I think everybody would do it the obvious way, and that would be it. If a time doesn't work for you, you shoot me an email, and as always, I'll fix it. I think we're used to how I do this. You agree? Right.
Yeah.
So let me give you a heads up on the final, which is going to be different. right? The final is going to be different. In the final exam, I will put on Canvas a PDF of your final. And your final is going to be of a different format. It's going to have the same stuff in it, but different format. Your final is going to have 2 sections. And the first section is going to be multiple choice. So all you will do is write on paper, number 1 is A, number 2 is C, number 3 is D, right? And then section 2 will be basically questions very similar, some probably identical, to what you've done in WebAssign, but you're going to do the working on paper. And so you're going to basically you're going to upload everything into Canvas, right? And you'll get 3 hours to do it.
Do you mean you're gonna have your answers on paper as opposed to entering answers in
Yeah,
WebAssign?
WebAssign will not even appear. So there won't be a
Okay.
WebAssign final. There will be a PDF. Now, I'm assuming that everybody knows how to open and see a PDF, right? And you will do all your questions on paper, and all I will basically see is, do you know the Canvas upload your working?
Yeah.
That's where it'll go, right? So that's just a little bit different, right? But, you know, to give you a heads up so you don't suddenly turn up on the day and say, what the heck's going on? But this test is just like normal. It's going to be WebAssign like normal and so on. Ben, question?
Are you going to be on Zoom for the final?
Yes. If nothing else, just to say to me, question 5 doesn't work. Could you check it? And then I'll go, oops, that plus 2x should be minus 2x, everybody. You know, things like that. I will try not to make it happen. Do you have any confidence that I will not make it happen at least once? No, okay. By the way, I have a fix for that. In the multiple choice, there are 5 choices, A, B, C, D, and E. E is some other answer. So if I screw up in a multiple choice, you pick E and move on. Right? So if none of my answers are the one you got, and you're 99% sure you're right, you just pick E. Okay. For the test, you're going to do a PDF. Someone put it in the mention there. So you're just going to go onto Canvas, right? And right in Canvas, you'll probably only see 2 things. PDF of test here, upload your working for test here, right? For PDF of final is here, right? Upload your working for final, because that'll be the only 2 things that'll matter, right, on the day of the final, right? So it'll be pretty clear in Canvas. You'll click on the PDF and you can see it. If you're a paper person, I guess you could print a PDF. It wouldn't be that hard. Show me your working, call it good. Right, back to the test. I think the test is going to be what you'd expect it to be, right? I don't know if there's really anything that you haven't done before.
That's
Any
still
more
gonna be at
questions?
10 to 11, right?
Our test is just going to be the usual 10 till 11, right? And the final's different, right? The final is on its own time slot and it's got 3 hours for you to do it. What else have we got? I'm good. Is there any other questions? Otherwise, it's bye-bye. Bye-bye is if you've got questions that you don't want to share with everybody, then I guess you could hang about for a second and I'll answer yours. Reese, did you figure out what you thought your issue was?
Yes, I'll present. Can I show it? Present my screen? Like, you can draw on the screen or something with Zoom.
I will give you permission to share your screen and you can do whatever it is you want to show me. And then I can
Okay.
get an idea of what you want. Okay. So you
Okay.
should be able to do it now.
Okay, whiteboard, okay, so, the function again was X, Y, E,
Uh-huh.
well, Y, Z, and, X, Z, yes?
Yeah.
Okay, so we're taking, okay, 1/2 X squared, Y,
Agreed?
yeah, yes, but we also have to integrate with respect to X, so that's 1/2 X squared Z,
No.
Oops.
That's
No, wait, never.
that's where your mistake is.
Oh, no, wait, no. Okay, so plus 1/2 xz squared and okay. So now we're gonna find the partial derivative with respect to x. So let's differentiate this. This gives xy plus
Check.
1/2 z squared. Like,
Why will it give 1/2 z squared?
look at this, 1/2 x. So we're assuming 1/2 z squared is a constant. So
That's your mistake. You're doing all three terms with respect to x. What you're going to oh, I see what you're getting at. Oh, Race, I see what you're getting at because of this term here.
yes.
Oh,
Why do we- What?
Then I know what I screwed up. It's not the math I did. This function, I believe, was 99% sure was going to be a conservative field. What you've just shown me, because it didn't work, is that this is not a conservative field then. So I've just managed to find a very symmetric function that is not a conservative field. So you nailed it there. I got you. So, I understand what you're getting at.
So yeah, that was the issue that was causing me problems. Anyways,
And
yeah.
you stuck to your guns like any good mathematician should, and you were right to. I made one fundamental assumption here. I assumed that this was a conservative field. I guess that is an indirect way of proving a function is not a conservative field, which is find the potential function and then work backwards and see if it matches. Right.
Yeah.
I
Anyways,
will keep this on if you don't mind, Grace, so that others can check
okay.
what you were doing.
Yeah.
That was really cool. My brain was not even thinking of that. I was thinking each one separately, which is not the case. When you differentiate, you do the whole package gets differentiated.
Okay. Anyways, have a nice day.
You too. Thank you for finding that.